So today we have third part of the tutorial. So Victor will continue from where he left off in the last lecture. So Victor.
Thank you. Thanks for coming back. It's good to see you. Now I am going in on reverse. Let me see. Okay, let me just review a few things. Okay, not so back. Okay, so we're talking about the result, a decoupling inequality that was very useful in extending the theory of empirical processes to the case of U processes, processes indexed by functions. And it was extended is by using the decoupling inequality, and then with the inequality one can transfer results for U statistics.
By the way, I think there's like some this going. That's a pushing sound. But I mean maybe the check the wall so that like this. How can you? Because like the sound is picking up, so
oh, okay.
Maybe like the wires loose somewhere.
Mm-hmm.
Check.
Maybe I loosened it.
Okay.
Okay.
Also, maybe don't touch this one because it might the sound might breaks up.
Oh, okay.
Do you want to move it a little lower? You should go
I guess it's fine, but like,
Okay, so I won't touch it. Okay, so this formula includes U statistics when you let Fij to be F, and also quadratic forms when you let Fij be Aij times Xij. So the result that I'm going to show you was important in the first, it was used in the first paper of Candes and Reck on matrix completion. So it was an important result for that. And also in developing the theory of U processes, which is an extension of the theory of empirical processes. Now, the reason why U statistics, the decoupling inequalities are useful is because we are going to replace the Xj. So we replace the Xj by Xj tilde. So we have two sequences, X sub I and X sub I tilde. They are independent copies of each other. Okay? Then this U statistic is adapted to F sub I, the sigma field of the X's. And we are taking an independent copy, X sub I tilde. Now, I want to point out that the one when you plug in tilde in replacing can be written as in this following way. So it's the sum j going from 2 up to n of tj of xj tilde. If you fix the x's, you think of the x's as constants, then when you condition on the x's, this becomes a sum of independent variables. So the results on empirical processes that were known at the time involve sums of independent variables. And so this allows one, once you have the inequalities, allow one to treat the case of U statistics as if they were sums of independent variables. And then once you use the inequality, everything slices like a cake. You can slice, like you can get the central limit theorem, the law of the iterated logarithm, can get convergence theorems using the results for sums of independent variables. So that's the reason why decoupling is helpful. Now, the main decoupling inequality that I will prove today is the following. So suppose that we have a convex function which should be increasing to have a general result. So the function should be increasing, convex increasing, and you will see why. So the expected value of the function of the norm of the sum of f sub ij of xi xj is less than or equal than 8, expected phi of 8 times the sum of fij of xi xj tilde. So this is a sum of conditional independent variables, and then you can use to bound this expectation, you can use this expectations for sums of independent variables. Now, these f's are in a Banach space, so that allows you to take supremums of functions over this, because we have a Banach space. So you have the Banach space, you can work with Banach spaces in this case, and that's what allows you to extend the theory of empirical processes to the case of U processes. Now, if the functions are symmetric, then the lower bound holds, but the constant is better, 1/4. In some applications, the constants are important. Okay, now, the lower bound cannot be true in general because of this example. If f of ij of xi xj is equal to xj minus xi, then the sum of this is equal to 0, because we have all I and j. And however, if we look at the symmetrized kernels, fij of hat of this, okay, taking the average, then it's symmetric. And so then you can apply the inequality. Now, this is the special case of random matrices. Well, actually, the special case of quadratic forms of independent variables applies as well. So this is what Candace and Rec used, a version of this inequality. Now, to prove it, we use a basic lemma. So this is like a warm-up lemma. So we are going to denote by E sub sigma of y as the expectation of y given sigma. Okay, where sigma is a sigma field. Now, if you have the proof of the martingale of the law of large numbers by using martingale arguments is based on this lemma, an extension of this lemma. So the lemma says that if you condition on the situation where you know the values of x1 and x2, but you do not know which value is the right one, whether, so then those are the C's. C1 is x1, x2, and with what probability a half, and C1 is x2, x1 with probability a half. Then the expected value of x1 given C1, given that you know the values but not the order, is going to be equal to x1 plus x2 over 2. This, this might be a little mystifying, but it's a simple fact. So to show you that, I'll write in the board a simple proof. Okay, so what you have is x sub I iid, and then you are going to look at the expected value of x1 given x1 plus x2, which is which can be found by the value of that is x1 plus x2 over 2. And the proof is, we know that since the variables are ID, the expected value of x1 given x1 plus x2 is equal to the expected value of x2 given x1 plus x2, which is equal to, so if I sum these two, I get 2 expected value of x1 plus x2 given x1 plus x2. So because I'm conditioning on the same variable, this becomes just x2, x1 plus x2, okay? And so
The 2 should be divided by, not multiplied. The 2 should be half.
the 2 should be a half. Yes, I shouldn't put anything. 1 second. You threw me a curveball. Now, can someone get me out of that curveball? Because I believe okay, yes, so this should be 1.
Yeah.
There's no 2 there. And then, so since I have the sum of 2, this is x1 plus x2. Now, what I'm doing is I'm taking this expectation is equal to this expectation. And therefore, if I add both, I have 2 expected value of x1 given x1 plus x2 is equal to x1 plus x2. Okay? Because they are equal. And then when I add, I end up with this, and then I can take the 2 to the right-hand side. Okay? Now, so there is an extension of this to the case of 4 variables, of 2 variables, bivariate. And the way it goes, so you see, I could have called this x1 tilde. And so what I'm going to do is I'm going to use that notation. So what I have is that the expected value, so I'm looking to prove, to get the following lemma. So I'm going to prove the following lemma using similar technique. Okay, so again, suppose that you know the values of xi tilde, but not which one is which. So that's what the zi's are telling you. Then, because the x sub i's and the xi tilde have the same distribution, that's the only assumption, that they have the same distribution. Not as j changes, but for a fixed I. I mean, so anyways, then the conditional expectation given f of xi xj is equal to the conditional expectation of fij of xi xj tilde, because I have IID copies. So the same thing for this and the same thing for this. Like in here I have IID copies, and that's why the expectations are the same. Then I use the same argument I use here to show that if I add these ones, I have this summation, okay? And so 4 times this, because I have 4 of these, 4 times this is equal to the sum of the fij xi xj plus fij of xi xj tilde plus, and so forth. So there are 4 terms, okay? So that's how it works. So it's very similar, but it took me a while to figure it out. You know, the lemma is very simple, but it took me a while to figure out how to set it up. And so there were decoupling inequalities for quadratic forms, but the extension required the extension of this lemma. Yes, question? Yes.
Yeah. Do you need that Zi to be that particular order with probability half? I think with any p and 1 minus p it should work, your argument.
I guess you're right, but I don't know what you would come up with. You know, I don't know if I can use that to do the replacement. You would get a different inequality. The fact that the value is 1/2, the probability is 1/2, is what allows you to consider this as a situation where you have the knowledge of the values of x1, x2, but you don't know which one is which. So that's what works, because that sort of symmetry is necessary.
I see.
Yeah, I think that's because symmetry is what. Yeah, exactly.
Any other questions? Okay. Now, if we let conditional expectation of y given c to be e sub sigma of y, and we take script x to be the sigma field of y1 up to yn, of x1 up to xn, I'm sorry, then, oops. So it's easy to see that this expectation is going to be the same as this, because the expectation, if you know all the x's, these become constants. So you're starting with this, with the function of xi, xj, and then, which is what you have here, and then you are adding the conditional expectations with tilde xj and f of xi tilde xj tilde. So this is a symmetrization identity. It allows you to symmetrize with respect to xi and xj tilde. Then, so you add them and subtract them, and you add the three terms and subtract them. So that's a basis for what we're doing. Now, notice that we have the expectation of 4 conditional terms. And that is helpful, because that's what the lemma works with. It's a different sigma field, but we have the form that we're looking for. Okay, so from the lemma, we have this, and so, this is going to be equal to expected value of under C of f of xi, comma xj, okay, plus equal, which is also equal to the expected value of given C, okay, expected value of C of f of xi tilde, xi, xj tilde. So just, you have all possibilities of xi and xj. If you assume that they have mean zero, the functions have mean zero, they are degenerate, which is the case on quadratic forms of independent mean zero variables, then the proof is fairly simple, and the constant is 4 under that assumption. So let me show you how that works. So here we have the expected value of the undecoupled sum, and that because the conditional expectations are 0, then this can be written, okay, this will become, this expectation is equal to this, because these expectations are 0. And then I am conditioning on x, on the x's. So I can take this expectation outside, this conditional expectation outside here, and I have the same thing, and then I use Jensen's inequality. So I take Jensen's inequality, and then I notice I have this lemma. So this is equal to the expected value of script C of f of xi xj tilde. So I'm changing the sigma field. I started with script x, used Jensen's inequality, then I went to the sigma field script C, and I have this in there. I'm replacing it because of that identity. And then by using conditional, I can take the expectation, the conditioning outside, because I'm conditioning with respect to the same sigma field. You couldn't do this if the sigma field was different as you add. But since the sigma field is the same, I can take it outside the summation, and then by using conditional Jensen's inequality, you end up with this. So the proof is fairly simple. Now, at the time, there were inequalities. So the first people that obtained decoupling inequalities for quadratic forms had to assume that the variables were mean zero. So the challenge was to get rid of mean zero assumption. And that was tricky. So the decoupling inequalities were known for quadratic forms of mean zero variables. Let me think. I think that was in 1984. And there were about, by the time I got in, there were about 100 articles on decoupling. So it became a very popular topic. So anyway, so I produced these inequalities for U statistics, and I was able to remove the assumption by using a very tricky trick, like trick or treat. Okay, so let's see. So that's why I'm showing you the next result. Okay, so the result is actually this one. This one. So this is what we started with, that the decoupling happens with a constant of 8. Okay? So let's see. So I start with the undecoupled sum, and then I add and subtract the terms that I just learned to add and subtract. And then in this case, I can use the triangle inequality. I add and subtract, and then I use the triangle inequality to make this expected phi of A plus B. Where this is A and this is B. Now, by convexity, I can show that this is equal to, so I write it as follows: expected phi of 2A plus B over 2. And using the convexity, this is equal to the less than or equal than the expected value of phi of 2A, no, of a half 2A plus a half expected value of phi of 2B. So that's what's at play here. So that's how we got here. So we are using the convexity property. Then there are a few more steps. So what we just did was this part. So we started with expected phi of the sum of f of xij, and by using the convexity and conditional Jensen's, we ended up with this, where that is A and this is B. Then we know that this expectation, okay, by using Jensen's inequality, I can take this expectation outside, conditional Jensen's. And what I end up is just the sum of f of x, fi xj, f of fi xj tilde, and so forth, which is basically, I replace the sigma field. Now I am working with the sigma field script f. And this summation without the 4 is equal to the 4 times the expected value of the condition of C. So I multiply the 2 by 4 and replace the conditional expectation of Fij of Xi Xj tilde. So that's how that happened. And then I use Jensen's inequality to take that outside. And so I have the first part of the decoupling inequality. So I can remove this by Jensen's inequality, conditional Jensen's. Then for this term, I have 3 terms. So I multiply by 3 and divide by 3. And then I use convexity. So then I have expected phi of A plus B plus C is less than or equal. These are non-negative. And it is equal to the expected value of phi of 3A plus C over 3. And by using the convexity, I can say that this is less than or equal than the expected value. Let me think. Oh, yes, I had 2 here. I'm working with this term. So it's 1/2 expected phi of 2. So then I replace this 2 times 3. So that's a 6. And then, so that's how, by using the convexity, I can replace this expectation is bounded from above by the expectation of each term times 6 inside. Okay, so the trickiest part, okay, not yet, I won't tell you that yet, but then for this one you use conditional Jensen's inequality, and you have Fij, f of xi tilde xj, which can be thought of as, you can replace, since the variables xi and xi tilde have the same distribution, you can replace this by f of xi xj tilde. And so that's the form that I wanted. So then the same thing, well, this one is already of the form I like, but this is the tricky part. And that's the thing, the hardest thing to come up with in the proof, because I want to replace this by xj, it is by xi. And so what I noticed was that I am conditioning on the x's, okay? So the x tildes are independent. Therefore, there is no conditioning, okay? And so I have the expected value of Fij xi xj. That's what I'm looking at. So now, since the variables since the tildes and the non-tildes have the same distributions, this is exactly the same as the expected value of f of xi xj tilde. Is that clear? That was the main trick of the whole thing. Well, aside from the lemma, one had to come up with a lemma, but then one notices this, and then so using conditional Jensen's on the first 2 terms of the second part, and I am here now. Then if I use Jensen's inequality, I replace this by xj, xi tilde is replaced by xi. So then I can use Jensen's inequality once I did the replacement. So instead of having this, I can put Fij of xi, xj tilde. So then I can use Jensen's inequality to come up with this. And then I have the other terms. Now, since the function is increasing, I can make this even bigger. You know, I can homogenize. I have 1/2 of this plus 1/2 of this. I can replace this by 8, and that becomes the expected phi of 8. You can, you know, there were some people who were very obsessed with the constants. So they found, like, there were some Polish mathematicians that found a constant of 7. You know, if you are very careful what you're doing, you can reduce it. So some papers were published getting better constants. Okay, so now where am I? Okay. Okay, so now this that was the first result on U processes, decoupling inequality for U processes, and then I met with a functional analyst, Stephen Montgomery Smith, who's at Missouri, whom I met because I went to see Burkholder. So I met him there, and then we became good friends, and then we started working on decoupling. But the decoupling that I had in mind involved tail probabilities. And so if you replace the expectation, you can get a tail probability bound. So for every t bigger than 0, you have this inequality, where this depends on the order of the U statistic. So here, this is a multivariate version. So you have xi, xi1 up to xik, and you replace by xi1 of 1, xik of k. Now, recently I noticed that for these functions, to make the proof more transparent, these functions should be exchangeable. That means to say permutation invariant. Because that sort of allows you to do the iteration. So the way the proof of this happens is by well, this result depends on the previous result for multivariate functions. But the result is obtained by iteration. So we start here. So the way to get the multivariate case is by decoupling this term. So you first decouple this term. Okay? So then it becomes a U statistic on the x's and the x tildes. The constant will be 8. Okay? Then what I do is I reorder this. So I put the tilde here, and then this is x. And so now it has the same type of form, except that I add over xi tilde and x, and over I and the i1 up to ik minus 1. Then I have the form, so that becomes a function f of the x's, so the vector of x's, and the xik, so it's the vector of x's. Let me think. And the ik, okay? So this is a summation of vectors. So it's the same form that I wanted. This one includes x tilde. I don't know if you can see that, but I can be more meticulous about it. But so I needed to take the outside. So I first decouple this way. Then to get the three, so there's a subtlety in the proof of the third order statistics, in that we need the symmetry to take this one to the beginning, and so then what I do is it becomes another U statistic that has the form that I like, and I decouple this one. I put double tilde. And then I do the same thing. I permute because of the symmetry. I permute, and then I put x triple tilde. So you see here I have xi tilde, xi, and then xi double tilde. It depends on the order of the U statistic that you're trying to. And so that's why by induction, in using the symmetry, you can end up with this. Okay? So now this symmetry, I didn't realize it until Percy Diaconis asked me. So he's working on problems like this as we are speaking. And so he wanted to know how to prove the case of 3. The case of 2, I showed you the full proof, and he wanted to prove the case of 3. And when I was preparing to show him, I realized that I needed the symmetry. Okay? The symmetry part. And so that's how we left it. So he needed that for his studies, and I don't know what he's doing. I wish I knew. I wish I could work with him on that, but you know, he was very secretive about what he was doing. He said that's going to be a thesis for one of my students. So I don't know when that will come up. You know, the consolation prize is that I'm working with Siva. Sorry, I didn't mean to. No, because we have an inequality, decoupling inequality for U statistics, that it's a much more general thing, you know, for arbitrary sums, which allows you to get inequalities of this type, not tail probabilities, but second moments, multivariate, okay? So he might be looking for something like that, and we have the best constants. So it's, you know, whatever. So you try to work with the best people, but if they are not available, you I'm sorry, I didn't mean that. I didn't mean to put it that way. I had already started working with you when Diaconis asked me the question. So, okay, I think I'm not going to get reimbursed. Okay, so anyways, that's the end of this lecture. So now, can we take a break, and so I get the other lecture going?
Sure. 10, 15 minutes?
15 minutes.
15 minutes.
15
okay.
minutes.
So
okay.
we start
By a question, by a statement, but by Joe Dube. I was visiting Burholder, and Joe Dube was around. He used to do hikes, and so I asked him if I can join him on his hike. And on one of those hikes, I asked him, what's a good problem to work on? You know, when you are young, you want to fish for problems, you know, because the main thing is the problem. So he told me there are results in harmonic analysis for harmonic functions over superharmonic functions, but they don't have analogs in probability. So that would be a good idea to work on that. And so that stayed in the back of my mind, and out of that I started, you know, all of a sudden I found out how to do it. Okay, so let's look at examples of self-normalized statistics. So self-normalized statistics literally take the form of AN over BN, okay, and AT over BT for continuous cases. Both AN and BN are functions of the observations x1 up to xn. This could be martingales, or it can be anything. Martingale differences, or it can be anything. So you're looking at ratios of functions of the same variables. That's why we call it self-normalization. The theory of self-normalization was developed, as I will describe later, for independent variables. So I was aware of the results for independent variables, but Doob suggested to work on the case of martingales. So one of the main benefits of using self-normalization, so as the sample size increases, since I am normalizing by the same variables, the things are not growing. Well, you have a constraint. So in particular, if you have one example is the sum, if these sub i's are martingale difference sequences, of these sub I over the square root of the sum of these sub I square. This is like the t-statistic, and this is related to t-statistics, as you will see later. But if the variables have infinite expectation or infinite variance, this tail probability will not be controllable, right? Because of you have a heavy tail. But when you divide by this, if there's a big d sub I, it is neutralized by the square root of d sub I square. So that's why self-normalization is so useful. Now, so examples of self-normalization are widely, there are several examples. For example, in the federal, the World Bank has a statistic that is used to check inequality of financial inequality between countries. How unequal are the countries? And that statistic is called the Gini coefficient. So what you do is you have in a country, you have individuals, and they have different earnings. So each one of these is like the earning of a person. And if they are all the same, this is 0. Okay? This ratio is 0. Now, if they are all different, then the ratio, believe it or not, is going to be bounded by 1. So the Gini coefficient is between 0 and 1. Now, the way this is done, you say that the countries are more similar. They are better. They have better equality when the wages or the salaries are the same, similar. But if the wages or salaries are not good, then in which case the Gini coefficient is close to 0. So if not, then the Gini coefficient will be close to 1. So every year the World Bank publishes a list of countries, and they list which one is more equal and which one is more unequal. This is a political thing. So if you're equal, that's good. If you're unequal, that's not good. So maybe for the purpose of loans, more unequal countries get less support because they are being bad. The US is not a very income-friendly place because there are people that have extremely high incomes and people with extremely. But in Europe, like Switzerland, it is fairly balanced. Okay, so then there's also the coefficient of variation, where this Sn is the sample variance, and so suppose you have non-negative variables, you have the sample variance over the sample average squared. This is the coefficient of variation, and it's the square of the coefficient of variation, which is a measure of spread. So you see, the variance is a measure of spread, but it can be affected by this. You get a different variance if you have different units. So if you have salaries in dollars, the variance of the salaries is going to be different than the variance in pounds. So there's no way to compare them. On the other hand, with this, the units cancel. So this measure of spread is important in that sense that it is not affected by the units. So I have a paper with a couple of students where we find the exact expected value of this. You see, this is a very difficult thing to study because it's not just an expectation, it's the expectation of a ratio. And there's a trick of Karamata that allows you to get the exact expectation in terms of the marginals. And so people, when they report the coefficient of variation, they report the sample. But the sample could be very different from the population coefficient of variation. And so by studying this, we were able to calculate the bias of the coefficient of variation, which is an important issue. Okay, so I guess this is a repeat of what I was saying a little bit. So the t-statistic is for IID normal variables with mean mu and variance sigma square. And so we have the sample average, the sample variance, and Gosset, our student, developed the distribution of this random variable. Now, so why is the t distribution important? So, we call these variables the normal variables, right? The Gaussian variables. So when Gauss was working on his study of the distance to the stars, okay, and every time he measured it, it was a little different. So he developed a model where you were adding, the assumption was that they were Gaussian, the distances, and then he found a way to, the estimate of the distance was then the average. And you could test hypotheses as to whether or not the variance, the actual variance of the distribution was a given number. However, okay, so science, the way it evolved was you needed to know what the variance of your variables was to do your statistics. However, if the sample size was small, even though the variables were IID, you could not estimate properly the population variance because the law of large numbers doesn't kick in that fast. Like if you have like 10 or 20 observations, the sample variance is not necessarily too close to the population variance. So Gosset replaced the population variance, which the C statistic or the normal curve is used to study this case when I put the population standard deviation here. Yes? So what Gosset did, he found a way of not needing the variance. So this allowed things to be data-driven. And, you know, we know now that machine learning algorithms are very important, and the improvement that happened, a big improvement, a big leap, was to go from parametric assumptions to non-parametric assumptions. So machine learning algorithms that are data-driven, where you don't make assumptions, because if you make the wrong assumption, you get garbage, you get the wrong thing. But if you don't have, if you are using the data to determine the algorithm, as opposed to including a parametric assumption, then you get better algorithms. So in recent time, using self-normalization, which is basically related to the t-statistic, people have been able to obtain optimal algorithms, which is not possible if you need to assume parameters. Because if you have a misspecification of the parameter, then you get the wrong algorithm. Okay, so that's the motivation between self-normalization. Now let us notice, so the self-normalization that I work on is not t-type. It takes the form, so let's replace x sub I by x sub I minus nu, that I'm going to call that as y sub I. So I will call an to be the sum of the y sub i's, and bn squared to be the sum of the y sub I squared. Then the t-statistic can be written as this sum, as this statistic. So it's the ratio of an over bn over n minus an over bn squared, which is a function of the self-normalized U statistic. Okay? So I just described what his towering contribution. It was a huge contribution to science, not to need to make the assumption of knowing the variance. And if you had so the t-statistic allows statistical inference about the value of the mean of a Gaussian distribution without the knowledge of the value of the variance, provided that one has a random sample from a target population. Okay. Now, everybody's familiar with the name of Efron, and he's the founder of the Bootstrap, and he has made a lot of statistical improvements. And so he developed a self-normalized inequality for independent symmetric variables. Okay, and then actually there were some other efforts for self-normalization of independent variables, and actually here is a slip of the tongue. So there were not really results for martingales. You see, this was done by my student, and I didn't catch it. So there were not results for martingales when I got into the game. There were very, very few by Dubins, and there was one by Marc Jor in France, and by Dubins in Berkeley, but the area was basically deserted. So when I got into the picture with other people, so I always tried to work with good people, and I was fortunate to have good people next to me. So I was working in Stanford, and all of a sudden I came up with an inequality, self-normalized inequality for martingales, because I obtained the exponential inequality, the moment engineering function inequality that I showed you, and that could be used to obtain that. And I got the case, Okay, I guess I'll tell you more about that story in a few minutes, once I get a little forward. I'm telling too many stories. Okay, so Bernstein's inequality. So Bernstein, most of the exponential inequalities that we know are based on the Markov's inequality, okay, and exponential bounds. So in particular this one. So where you have a sequence of independent variables, and if you assume that they have mean zero and variance sigma square, if we let the cumulative variance to be v sub n, if there is a constant, so if these variables do not grow too fast, so the kth moment is bounded by this constant, well, by this function of k times the variance, okay? Then Bernstein's inequality is that this is the probability of the sum of the x sub i's bigger than x is less than or equal than e to the minus x squared over 2 v sub n squared plus cx. Now, so the first inequality in self-normalization that I came up with was the following. Suppose that you have a martingale difference sequence. And let's assume that it's mean zero martingale difference sequence, conditional variance finite. V sub n squared is the sum of the conditional variances. And there is a constant, the analogous assumption in the case of martingales is this. Then for all x and y, the probability that the sum of the d sub i's or v sub n squared, the conditional variance, so v sub n is the conditional variance, bigger than x, 1 over v sub n squared less than or equal than y, is going to be this. Now, this is a sharp extension of Bernstein's inequality for independent variables to the case of self-normalized martingales. And the reason is because if the variables are independent and you let, so then this is a constant. You let the constant to be, this constant to be 1 over y, then you have the same inequality as in the previous slide. So it's a sharp extension. Now, so I went through the proof of this inequality, except for the g. I didn't show you how to do the g, but that's okay. So you see, the exponential inequalities that one obtains is the probability of the sum. So the way the proof goes is you have the probability of the sum. The probability of the sum of the, if you have martingale different sequences, sum of v sub I bigger than x is going to be less than or equal than e to the minus lambda x times the expected value of e to the lambda summation of d sub i's. Now, okay, so what I do, the proof goes is, now I have martingale different sequences, okay? So in particular, I want to extend to the case of self-normalized martingales. Then this will be minus lambda x. V sub n squared, right? So I can move this on this side, and then this will be x v sub n squared multiplied by minus lambda. So now, using that inequality with g to be this exponent e to the minus lambda x b sub n squared. So this is a function of the d's. It's a function of the conditional variance. So when I decouple there, I can replace that by the square, which is the same random variable squared, and the decoupled ones. So the decoupling then becomes the expected value e to the minus lambda x times the expected value of e to the minus 2 lambda summation of y sub I minus lambda x v sub n squared. Okay? Because that's twice, so that's a square. Now you can complete the squares and pretend that this is a constant. Because you condition on, so we have the inequality. Now you condition on the d's, on the sigma field of the d's. So it's the expectation of the expectation. You then so you are conditioning on the sigma field of the d's, so this becomes a constant. And by the property of decoupling, this is a sum of conditional independent variables. So then you can use the result for independent variables to bound this quantity. And this behaves like a constant, so you can then do the optimization. So that's how the inequality works. So you are replacing, so basically most of the exponential inequalities for sums of independent variables or martingales were extended by using this technique to the case of self-normalization, where the self-normalization was by the conditional variance. Now, so I obtained this result when I was visiting Stanford. And I was visiting TLI. And my advisor, Michael Klass, you've heard a lot about him here. So anyways, he was in Berkeley. So when I got this one, I said, well, what should I do? You know, I want to deal with the case. So this is this summation of v sub I over v sub n squared. This is a random variable associated with the law of large numbers. Okay? Now, what I thought was, well, the next step is then to v sub n, take the square root. And these variables is associated with what? With the central limit theorem. So I propose to Lai and Klass to work with me on mining this question. So I had two top-notch probabilist mathematicians working with me. It was a very exciting time. So I would go from Berkeley, talk to Mike Klass, he could tell me some things, then I would go to Stanford, talk to TLI. So I was ping-ponging between, you know, I would contribute my part, and then they could contribute their part, and it became an industry. It became very exciting. So, so what I'm going to show you is something that I developed with Klass and Lai. Okay, let's see. Now, okay, so in doing self-normalization, the key assumption is this one. So to get inequalities for the ratio of A over B, which is the self-normalization, we assume that we have a pair of random variables, no matter what the dependent structure is, but with this, assuming this condition. Okay? I'll show you many examples of this. So in particular, I'll show you an inequality for moving averages, the growth of moving averages. So to give an example of situation where this is obtained, and that is in the context of moving averages. Oh, the talk is over. Okay. Okay, so suppose that you have a sequence, a moving average, an autoregressive Gaussian process. So y sub I is equal to y sub I minus 1 times alpha plus epsilon sub I. Y sub 0 equal to 0. And alpha is a fixed number, which is an unknown parameter, and the epsilon sub I is IID mean 0, normal 1. So this is an important random variable in the study of time series. Now, we want to find the MLE, the maximum likelihood of estimator of alpha, and we want an exponential inequality for the maximum likelihood estimator. And voila, the maximum likelihood estimator is a self-normalized statistic. So, in particular, the log likelihood function, if this is the density of y1 up to yn, can be written, the logarithm of the density is the sum, j going from 1 up to n, of yj minus alpha yj squared over 2 minus n log 2 pi. Now, when you take the log likelihood, the derivative of the likelihood and equating to 0, solving for alpha, we get the maximum likelihood estimation of alpha, which is alpha hat and turns out to be this sum. So here we have the sum of yj over the sum of yj minus 1 squared, which can be written, because of the definition of yj, it can be written this way. Now you can separate the sums and you end up with alpha plus this sum. Now the interesting thing is that this is a martingale now, because you see epsilon j is independent of the yj minus 1. Okay? So we want to find how far is the maximum likelihood estimator to the parameter of interest. We want to test hypothesis about the parameter. You assume, you say, is alpha this size or this value? And you can use this random variable to test it. So self-normalization is useful in testing the hypothesis of alpha equal to a given value. I'll show you how. Now, there is the random variable at the bottom was the sum of the yj square, minus 1 square, which is equal to the sum of the conditional expectation of yj minus 1 epsilon j square given fj minus 1. And that's what I'm going to call b sub n square. So this is b sub n is the conditional variance of a sub n. So then the alpha hat minus alpha is equal to an over b sub n square. And because I have a super martingale, the expectation of this is less than or equal than 1. This is an easy exercise on time series, because you have mean 0, so this is less than or equal than 1. So this is a martingale, and then using the optional sampling theorem, we have that the expected of mn is equal to the expected of m1, and this leads to the situation that this is actually equal to 1, but it's less than or equal than 1, which is what we call the canonical assumption. Okay, so I gave you an example of random variables which satisfy this condition. So now in our study we treated the case of lambda real plus or minus infinity, lambda bigger than or equal than 0 or lambda in a range. Depending on what you're trying to do, the different ranges are useful. So this is useful for inequalities for the central limit theorem, and this one for inequality for the law of the iterated logarithm. I will come to that later on. Okay. Now I'm going to show how to obtain the canonical condition, the self-normalized inequality, this self-normalized inequality. So suppose that the conditional, suppose that the canonical condition is held, then the probability of a over b squared bigger than x and 1 over b squared less than or equal than y is less than e to the minus x squared over 2y. So this is a very beautiful inequality, I think. And I don't know that you can do better than this, but anyways, you know, Aditya Ram that was here before, he might have a better one by now. So, but anyways, this is beautiful. And it has been used widely. So the key to prove the inequality, so I'm going to give you a full proof of the inequality so that you get a sense as to how to prove self-normalized inequalities. So suppose that you have S, a measurable set. Then the probability, so here I'm going to teach you how to do better than Markov's inequality. So this can be any set. Then Markov's inequality, the typical thing will be to take the expected value of e to the a minus e to the minus x b squared. But if you keep the indicator, then you have something better than Markov's inequality. So in particular, let me just, you know, that might confuse the issue, but so if you look at probability of a bigger than x, you have Markov's inequality typically is written like this, right? Now, a better inequality is the one when I put the indicator of a bigger than x. And the self-normalized inequalities were obtained because I had a sharper bound than Markov bound. Is it clear how it works? So I recommend that you consider that. Now this is what allowed me to keep this indicator, is what allowed me to obtain sharp exponential inequalities. Okay, so let me show you the entire proof. The entire proof is basically 5 lines. So we have probability of a over b squared bigger than x, and s is equal to this. We exponentiate. Then less than or equal than the inf over lambda bigger than 0 times the expected value of this. So you take lambda, multiply by lambda, and then exponentiate, and then use Markov's inequality, the improvement of Markov's inequality. Then what you do is you complete the squares. So by subtracting lambda squared over 4b squared and adding it, we end up with this formula. Now, the other assumption of this course is that you know Chebyshev's inequality or Holder's inequality. So that's what I'm using here. So that's fair game. And so this is less than or equal than that, square root times this square root. And this is less than or equal than 1. Okay, so.
Is the reason the indicator function is in one and not the other?
Oh, well, I could have put it there, but it doesn't give me anything. And you know, the canonical assumption is that this expectation is less than or equal than 1. And if I keep it, it could still be less than or equal than 1. So I don't need it. But I kept it here. And this allows me to, S will become a constraint. So this is where we are. Now, this is a better inequality than perhaps what Randas does. Because you see, so I have probability, if I minimize over lambda, by completing the squares, I get with this. I get this expected value of e to the minus x squared b squared over 2 times this indicator. Okay? Now, if you erase the indicator, you get something which is, you know, if you know the distribution of b squared, then you can calculate this. And so you get what I think is a better inequality than self-normalized inequality. This is a better self-normalized inequality than the one where I take S to be the indicator of 1 over b sub n squared less than 1. So, I mean, that's in my paper. And